So before we start with Chapter 9, anybody have any questions remaining over, what did we do last? Section 8.4, which was confidence intervals for proportions, and then sample size estimates for confidence intervals for proportions. Any questions on that stuff? Okay. I've been saying this now for a while, but I'm going to say it again. The thing that I don't like about the Hawks Learning System homework questions is they never make you interpret the confidence interval, and they don't make you understand the concept of what a confidence interval is. They just say, give the critical value, give the standard error, compute the interval. Boom, good. Now you go on to the next one, you do the same thing, right? So that'll get you through the nuts and bolts of what you got to compute for the next test. But just know, you've got to do the interpretation as well. Right? The homework problems in the back of the sections in the book have the interpretation stuff. They'll say compute and interpret, but on the Hawk system, I understand why they don't, because it's hard to incorporate letting people enter a sentence and then grade it. You know, how do you do that? So usually they would make them into multiple choice or something, but they just didn't do it. So I will do that, and I want you to be prepared for the kind of questions you're going to get on the test. Right? It'll be a little beyond what's in this homework system. All right, so we ready to start Chapter 9? We're not going to do the last section of Chapter 8, which is confidence intervals for variances. That's something that you can do without, at least for a while. So we're going to jump to Chapter 9, and we're going to start in Section 9.2. 9.1 is the sigma known case. And like I said before, that's never going to be practical, so we're going to do the sigma unknown case and just jump right to that. Okay? So, comparing two population means. All right, so when it's a means problem, and it's confidence intervals, or Chapter 10 hypothesis tests, what kind of critical value do we use? If it's a means problem, we use Z or T? T. That's all I heard people saying, Z. No, it's not Z. If it's a proportions problem, it's Z. If it's a means problem, it's T. Now that's why I don't like doing the sigma known case, because you start with a Z if sigma's known, but as soon as sigma becomes unknown, then you have to switch to T. So I'm just, from now on, if it's a means problem, think T. If it's a proportions problem, think Z. All right? And we're going to be using the automatic functions in our calculator. So there is a Z interval in the calculator. We won't ever use that. We'll use T interval for means, and we'll use one prop Z int for proportions. Okay? So when we go to compare two population means, things change a little bit as soon as you go to compare two means instead of a confidence interval on a single mean. And the main change is that now it's the difference between the two that is of interest. Before it was, what is the mean? That was what is of interest. Now it isn't the mean for either of the two populations. It's the difference in those means. Okay? So I'll go through an example here in a minute from our data that we collected. We all know that the average height of males is higher than the average height of females. But how much higher? Well, we can put a confidence interval on that difference and say, well, I'm 95% sure the difference is in this range. Okay? So that's what we're going to be doing. So the point estimate for the difference in the population means, now the difference in population means is mu1 minus mu2. So that's the population. And in this case, population difference in means. The point estimate is x bar 1 minus x bar 2. Sample estimate. So everything looks just like it did before. All the formulas, all the symbols, everything's the same, except now we put subscripts on them. The subscripts are just to keep track. Oh, I got 1 one population and the second population. Now, what you call population 1 and population 2 doesn't matter. It's arbitrary. So I got males and female heights. I could call females sample 1, males sample 2. Doesn't matter. But if I reverse them, I just need to be consistent, right? So that when I do my interpretation in the end, I get it in the right direction. All right? So we'll go through some examples like that. So the book, all books, not just this one, but all books go through 2 cases. We're only going to learn one of those cases. So I've gone into the Hawk system and I deleted out all the equal variances case. So pooled sample variances. Now that you have 2 samples, you're not only going to have 2 different means, x bar 1 and x bar 2, you're also going to have an S1 and an S2 for the standard deviations. Right? So the book goes through 2 different cases. Can you assume they're equal, or can you not assume they're equal? And we're just going to do the not equal case. So if they were equal, you'd do this pooled sample variances thing. Ignore it. I put down here, at Washburn, we're not going to mess with this. All right, so I left it in there just to show that. But so anytime you do a confidence interval, remember, confidence interval is point estimate plus or minus what? Stay more general. T-critical is right for a means problem, but just in general, a critical value, right? A critical value times standard error of the point estimate, right? All of them look like that. So the point estimate we already did. That's x bar 1 minus x bar 2. Critical value, we know it's going to be a t, but if you have a t, you have to know it's... What do you have to know to get the right t critical value? Okay, you need the confidence level, the percent confidence level, but what else do you need? Which you don't need for z. Where do you get t critical values? From a t table or in your calculator, what function?
Inverse t.
Inverse t, good. And when you use inverse t or the t table in the back, you have to input what? Degrees of freedom. That's what I was trying to get you to say. So we have to know what the degrees of freedom are. Right? Well, now it's a 2-sample problem. If it was a 1-sample problem, degrees of freedom are n minus 1. Now it's a 2-sample problem. Ooh, so how does it work? Well, again, you get different degrees of freedom for the 2 cases. For the unequal variances case, what the book says, minimum or smaller of, how about that? It's a less technical word. Smaller of n1 minus 1 and n2 minus 1. In other words, whichever one has the smaller sample, then you use the degrees of freedom from that sample for this degrees of freedom. Right? The calculator uses an uglier formula. How's that? Uglier formula, which I'm not even going to show to you. It's built into the calculator. It'll output, it'll say degree of freedom equal, and so you can read it off of there. But it's a nasty formula, and it's not really important that you know how to do it. And we're going to go into the Hawk system here in a little bit and work some of those problems so you see how they're going to ask things. And I was real worried that it might not count things where you use the calculator to compute because it's using a different formula. But it went ahead and accepted them all. So somebody's already, if you click on show me how to do it, if you miss it, then it shows you how to do it using this. But if you do it with your calculator, it doesn't use this, it still is taking those answers. Right? But we'll demonstrate that. Okay? So the margin of error, this whole paragraph, you don't have to read it right now, but this whole paragraph basically says central limit theorem has to apply. Remember the assumptions? Well, now you got two samples. So the assumptions have to apply to both of those samples. So both samples are at least 30, or both have approximately normal distributions. And then what's the other assumption? Remember the whole thing I went through last time in class about you guys use convenience samples? Has to be random samples. So both populations, blah, 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 independent, simple, random samples. So there's another word that's added. This is not in the central limit theorem that you're used to because we only had one sample. But now we've got two samples. So for what we're going to do, we have to be able to assume those samples are independent. What's independent? What does that mean? One doesn't affect the other. What about our sample of males and our sample of females? Would those be independent? Yeah, they'd be independent, right? What about, what if I take a survey and we used smoking. So I do a survey on proportion who smoke, right? But I decide to save my time, I'm gonna ask both the male and the female in each house. Right? So I go to houses with married couples and I ask both the female and the male, are they smokers? And then I want to compare male proportion who smoke to female proportion who smoke. Are those independent samples? Males and females? I'm getting some nodding, yeah, they're independent. Some saying no. Right? You said no. Why? Why?
Because you're making an inference from the male data.
Well, I'm going to make an inference from any kind of data, but so go a little further with that. Laura?
Probably if one of the people smoke, the other one
Okay.
so it's not
Exactly. So there's information. If I know that the male in the household smokes, then I have information about the likelihood of the female smoking. Now, not every couple where one smokes, the other one also smokes, but the proportion is higher. You can show that, right? That it's more likely that the female will also smoke if the male smokes. And if the male doesn't smoke, it's less likely the female will smoke, right? So those would be paired samples. So dependent samples we'll often refer to as paired. If there's some logical way you can pair the two observations together, then they're dependent samples. Usually it happens when you take the same, can I start that sentence over? Usually it happens when you measure the same subject twice. You would have paired observations. So like a before and an after thing. If I measure your knowledge of statistics on the first day of class, and then at the end of the semester I measure, using the exact same exam, I measure you again. So I have a pre-test and a post-test. Those would be paired observations. I pair your pre with your post, and it's the difference between them that I'm interested in. Right? But if there's no natural way to pair, you can always pair them just by, hey, I think I'll stick this one with this one. But if there's not a natural way to do it, then they're independent samples. Okay. That's probably more than I needed to say on all that. But it is an important distinction because in the next section, we're going to do dependent samples ones. And so then on the test, you have to be able to read a paragraph and know which case you got. It's not going to say. Right? Okay, so here we go. T critical value, standard error. T critical value, standard error. So those two things multiplied together, as always, give us the margin of error. Now, the T critical value out here, this is where they say level of confidence. Oh, they haven't given degrees of freedom yet. It'll be on the next slide. But look at the standard error. That should look a little bit familiar, but more complicated than what you're used to. If there's one sample, the central limit theorem tells us that the variance of x bar is sx squared over n. So that the standard error which is the square root of that, is Sx over the square root of n, right? So the variance of the sum of 2, actually it's not the sum of 2, it's the difference of 2, but when you square things, the minus gets squared, so you're adding the variance of the first plus the variance of the second, then taking the square root after you add them together. Right? So, there it is. If you take a higher level statistics course, we go more into the theory of why that's what it is. But for now, you just have to kind of trust me. But it makes sense intuitively that you would have to account for the variability in the first sample plus the variability in the second sample, even though this is a difference. A very common error is just to say, oh, well, this is x bar 1 minus x bar 2, so it's a minus sign in there. But it can't be a minus sign in there. It's variability. You got two samples that each have their own variability, so you have to add the two variabilities together. Doesn't matter if you're adding or subtracting them, you still have two random variables. Okay? All right, so that's the standard error. Then to get the degrees of freedom, like I said, it's the smaller of n minus 1, n1 minus 1, and n1 minus 2. So I've added this little red sentence. The formula in our calculator uses the more complicated formula, but it's built in. You don't have to know it. And I'll demonstrate that as soon as we get to a problem. All right? So let's start with this one. And we're going to do this one all the way out, the hard way. And then we're going to do it with the built-in function in your calculator. So get your calculator out and enter sample 1 into L1 and sample 2 into L2. So L1 and L2. Okay? And these are on the PowerPoint slides that'll be posted on D2L. So this is, can I tell what slide number? This is slide number 9. So if you get confused about what the numbers were in your notes, you can go back and look it up. Yep. Oh. Guess what? So did I. Darn it. Yeah, just look off somebody else and... So I can't really yell at you for forgetting yours when I forgot mine too. But. Did everybody have them entered now?
Pull that down real fast.
Hard to see?
Yeah.
Okay. Okay. I got to stand so the camera will hit it. There we go. So what we're going to do, and some of the homework problems, this is what they're going to give you. Right? They'll just give you the stats. Sometimes they'll give you the data like this. And remember, there is the option in the calculator. Okay, so like I said before, everything is the same symbol, just has a subscript of 1 or a subscript of 2. So somebody go 1 var stats on L1 and tell me this. The rest of you do 1 var stats on L2 and give me these 3. Who's got L1?
3, 6.
Okay, 2 places is good enough. S1. Standard deviation. You're used to SX, but it gets real cumbersome to say SX1 with a string of subscripts, so then we just say it's S1. 2.46. Okay? And then sample size is 11. Okay? And then what about X2? Or sample 2? Has anybody got that? You got it?
I did.
L1.
You did L1. Who did L2? I should divide the room in half. You got L2?
Yeah, 11.3, and then standard deviation is 2.406.
Is it 11.30?
It just says 11.3.
Okay, so it is. I'm going to put the 0 just so that I'm not doubting whether I have the same number of decimal places. Then S2?
2.406.
406. And then 10. Okay? Okay, so first of all, the eyeball test. Look at the mean in the first sample compared to the mean in the second sample. Does there seem to be much difference? No, they're pretty close, right? So I don't expect that my confidence interval for the difference will be very far away from 0. It should be fairly close to centered around 0. So now, what is the point estimate? So x bar 1 minus x bar 2 is 11.36 minus 11.30, which is 0.06. Right? So now you compute the standard error of x bar 1 minus x bar 2 using this formula. Okay? Compute that standard error. I wish I had brought my calculator because I don't know the right answer, although it'll be on the next slide. And I'll give you a little bit of warning on this. This is a big, long formula, so it's easy to get parentheses in the wrong spot or whatever. Make sure that the square root applies to the entire sum. You don't take the square root of just the first one and then add the second one to it.
So the sum is under the square root?
What's that?
So the sum is under the square root?
Right. The sum is everything is under the square root. You got 1 point something?
I got 1.06.
It seems small to me, but no, I guess it's being divided by 10. I was thinking, well, it ought to be kind of the average of these two. But these are standard errors, those are standard deviations. So it has the over in part. So that sounds about right. 1 point what?
06.
Give me one more place. 063. Okay? Now, T critical value. Well, let's go ahead and do the T critical value the way they say to do it here, using the minimum of the two sample sizes, which is 10. So the degrees of freedom would be 9. So degrees of freedom equal 9. So T crit is equal to, and they said 95% confidence. Yes?
How do you know how to use for the first L1 for the degree freedom?
It says use the smaller of the two. Right? So since 10 is smaller than 11, we use that one. If they had been reversed. Okay, so T crit equals, what do you enter? If you use inverse T function, what do you enter for the first thing? Which is 0.025. Half of alpha. Right? And 1 minus the confidence level is alpha. So alpha is 0.05. Half of that's 0.025. And then degrees of freedom, 9. And what's that give? Say it again.
2.36.
2.262.
Yep.
And she said negative, and that's what the calculator will give you is a negative, but you can ignore the negative, right? It's number of standard errors, so we just go 2.262 standard errors. Since you're doing plus or minus in the confidence interval anyway, it doesn't matter whether it has a negative. Okay? So now we're ready, finally, to get the margin of error. What's the margin of error? 2.262 times the standard error. Now, I will warn you that I'm intentionally not keeping a lot of decimal places as we're going through this, just to make it easier to keep track of. But when you do intermediate steps, try to keep as many places as you can. And they're usually just in your calculator, so it's not hard to keep them. Because if you round every step, you have so much round-off error by the end that it counts it wrong. Right? If you only round at the end, that's better. Okay, so who's got that answer?
2.45.
2.405. Anybody disagree? All right. I think we're ready to do the confidence interval now. So what's the confidence interval? What do you do with the margin of error? You subtract it and add it to the point estimate. The point estimate is here, right? The difference in the two sample means. So the confidence interval is 0.06 minus 2.405 to 0.06 plus 2.405. And I can't do that. I can do this one in my head. That's 2.465. This one?
Negative 2.345.
2.345. Okay? Now, interpret that interval for me. What does this mean? When I say interpret an interval, what does that sentence always start with?
We're 95% confident.
We are 95% confident that...
The confidence interval for the difference between. So, for 2.
For the difference. This is a confidence interval on the difference. A common mistake on that interpretation is people say, well, I'm 95% confident that... And did they even tell us what this scenario was?
It says confidence interval for the difference between the two populations.
Yeah, at the top. But I was just looking to see, were they talking, what's their scenario here? But they didn't even give a scenario. They just said sample 1, sample 2. But if we're doing heart rates or pulses or whatever, it's not that we're 95% confident the mean heart rate is in here. It's the difference in the mean heart rates that's in there. 95% confidence that the difference in the population means is in that interval. Okay? Now, what do you notice is in that interval? Negative values and positive values, which means zero's in there, right? It straddles 0. If it straddles 0, then can we rule out that there's no difference in these samples? 0 is in the interval, so 0 is a plausible value for the true difference. So that says, well, we don't have enough evidence to say there's a difference in these two samples, or in these two populations.
Is it possible to get one that doesn't have a negative?
It's very possible. We'll show that in just a second. Okay, now, everybody got that? Go back into your calculator, press the stat button, go over to tests, and go down to 2 samp t int. So go stat, tests, and then down to 2 samp t int. So what does the 2 stand for? Two sample, right? So 2 sample, t because it's a means problem, and int because it's a confidence interval. 2samp t int. Got it? Now at the top, first thing it asks is input. It'll say data or stats. So which should we use? Data, because we have our data in lists. If all I gave you was this, these 6 numbers, then you would select stats, and it'll give you a place to enter those 6 things. Okay? If either way you do it, you get the same answer. Right? But select data for now. Okay? And then it'll ask you where your data is. It'll say list 1, list 2. Is that what it says? Okay. So list 1, list 2. Put L1 and L2. And then what's the next thing it asks? Oh yeah, freak 1 and freak 2. And those should be 1s. Right? We didn't get our data from a frequency table, so we don't have to worry about that. So just leave. That should be the default. And then next is C level. Confidence level, so enter 0.95. And then you get this question pooled. And it says yes or no, and we want to always select the no. Right? And the reason that I teach it this way is because there's nothing wrong with pooled estimate. There's nothing wrong with that. But in the case where the 2 standard deviations are in fact equal, where it would be okay to say yes, you get the same interval either way. So yes works when they are equal. No works whether they're equal or not. So just use the no. Right? And books don't teach it that way, but for an intro stat class, I think that's fine. So just always say no to the pool question. Now go down and hit calculate, and you should get this same interval, but probably to more decimal places. No? Well, then we did something wrong along the way. How off is it? Is it off just by round off error?
Negative 2.162.
2.162. Degrees of freedom, yes. That may be the difference.
18.88.
Yeah, I'm looking at this. 2.289. 2.289. And the degrees of freedom are 18 something? 885? Okay, so that's approximately 19. Go back into inverse T and do the T critical value for 19 degrees of freedom instead of 9 degrees of freedom. And the reason it's so close to the sum of the 2 degrees of freedom is because the 2 standard deviations were so close to each other. So we clearly could have said yes to that question because they're almost equal.
Why is it 19? Why is the degrees of freedom 19 though?
Oh, I erased it. Remember I had the uglier formula? That's where it's getting, right? If they are equal, and I'm not going to make you know this, but if equal, the degrees of freedom are N1 plus N2 minus 2, which is just N1 minus 1 plus N2 minus 1, the sum of the 2 degrees of freedom. Well, in this case, that would be 10 plus 9, or 19, right? So that's where the 19 comes from.
So does it do that on the homework?
So far, it's always accepted either way. I want you to use the degrees of freedom that the calculator gives, but the intermediate steps, they're going to ask you, what's the T critical value? So far, it has accepted both. If I did it this way with the minimum, it took it, said, hey, good job. If I did it this way, it took it and said, good job. Right? So now, what's the T critical value if you use 19? 2.09. Give me one more place. 0.93. If you substitute that in right here, that probably explains the amount of difference. So I don't know if it's worth going all the way through, but that's when you use the built-in calculator function, it's always going to use the more complicated formula, right? So you won't always match exactly what you got. You'll get an interval that's a little bit narrower, right? Notice this one is narrower because the degrees of freedom are higher. And as degrees of freedom get bigger, remember the t critical values get smaller and smaller until they approach the normal z critical values. So they're getting a little bit smaller as your degrees of freedom go up. Right? This is the max that it could be. Then if you use the minimum, the calculator will have some number in between those two. And how far in between in either direction it is depends on how different your standard deviations are. These are really close, so we got back to the 19. Okay? I know that gets confusing. How do I know when to do what? Which is why I teach it. So we're just going to always do the same thing. And I check the Hawk system, and it seems okay with that. So let's go clear to this one. Here's from your data, female height and male height. We had a sample of 226 females, a sample of 139 males, and we had a mean height of females of 65.28 with a standard deviation 2.95. And for men, mean was 71.45, standard deviation of 2.97. So go use your automatic function in the calculator, 2samp t int, and give me the confidence interval. Let's do 95% again. So 95% confidence interval for difference in mean heights for males and females.
Well, we don't have this stuff for L and L2.
No, you sure don't. And that's why I picked this one. So now you don't select input as data, you select input as stats. And the screen will change. And it will ask you for these 6 numbers. You got it done already?
Yeah.
Okay. So when you compute that confidence interval, you get negative 6 point, go ahead and read it to me, Alicia.
798.
798.
Negative 5.542.
542. Okay? Everybody get anything different? Everybody's agreeing with that? Okay. Interpret it.
We're 95% confident.
We are 95% confident.
That's the difference between males and female height is half.
Okay, that the difference between the mean heights of males and the mean height of females is somewhere in that interval. It goes negative 6.8 to negative 5.5. Now put it in English. Pretend you're talking to my mother, who doesn't know anything about statistics. What is this saying? Are men taller than female? How much? The fact that they're negative tells you what? Which group is taller? The one you called sample 2 must be the bigger number. You took a small number minus a big number, you got negatives, right? So again, it doesn't matter which you call sample 1, sample 2. If I had reversed them, I would get this. And you can check me on this if you want, but you know I'm always right. You would have got this. Notice it's the same numbers without the minus sign, and they flip right? So, reading either one of them, I am 95% confident that males are somewhere between 5.5 inches and 6.8 inches taller than females on average. Okay? That's how you interpret that. Okay, so let me pull up the Hawkes system. Oh. It timed out on me before I could get back to it, but that won't. So I'm going to pull up the homework, and I'm going to go right to certify. And I actually don't want to do this one. I want to do the next one. Can you skip them? Not in certify? Just get it wrong? Okay. 0. Submit answer. You're not very smart. Display answer. Okay, next. And see, it's going to do the same one, and it's the step 2, so... Yeah, this is frustrating. Next time I'll go into practice because you can do skip, right? But oh, so now I'm already failed. God. Let me start this over. How do I get out of here and go back to dashboard? There we go. So go to here. Sorry about that. So I'll do practice. I want to skip to the second question. Skip. There. Okay, so let's work this together. We've got just about 8 minutes left. It says Land's Bend. Kind of like Land's End. Land's Bend sells a variety of outdoor equipment and clothing. The company sells both through mail order and via the internet. Random samples of sales receipts were studied for mail order sales and internet sales, with a total purchase being recorded for each sale. A random sample of 17 sales for mail order had this mean and this standard deviation, and then a random sample of 9 sales for internet sales had this mean and this standard deviation. Using this data, find a 95% confidence interval for the true mean difference between mail order and internet purchases. Assume population variances are not equal and that the two populations are normally distributed. Right? So they're giving me the assumptions. All right. So first thing it says, find the point estimate that should be used in constructing the confidence interval. Do it. What's the point estimate? I'm going to write down the given information. The first sample, it said N is 17, X bar was 83, and X bar 1. I need my subscripts on those. And then standard deviation was 20.25. And then N2 was a sample of 9, X bar 7260, and S2 was 2375. And we're supposed to do 95% confidence. So what's the point estimate that we need? X bar 1 minus X bar 2. So give me that. What'd you say? 10.4. Okay, 10.4. Correct. Next step. Find the margin of error used in constructing the confidence interval. So here's what I want you to do. You're going to use the calculator, And what's that?
We'll take the mean.
Yeah, but the problem is that what she said was, oh, we'll use the calculator to give us the interval, then we take the upper bound minus this point estimate, and it'll be margin of error. But it won't give it to you to 6 decimal places. So you're going to have to punch it all out. But I want to get the degrees of freedom from the calculator. Right? So go back in, do 2 samp t int, enter these 6 things, and then we'll write down what the degrees of freedom are that the calculator says. T, yeah. 2 samp t int.
I get 33.93.
33.93 for degrees of freedom.
I got 14.
Oh yeah, it has to be a number that's in between 8 and the sum of, so it's 14? 14.28, so we'll call that 14. Okay? So we went into 2 samp t int, said no to the pooled question, did it, and then just read the degrees of freedom. Now go inverse t of 0.025 with 14. I'm going to run out of time before we can get this done, but 2 point what? 145. Okay. And then the standard error, let's go over here. Standard error is the square root of 20.25 squared over 17 plus 23.75 squared over 9. And then we're going to take that answer times the t critical value to get the margin of error. And then when I was working this before class, the next problem I went to, I didn't pay attention, and it asked, find the standard error. And I found the margin of error and plugged it in and went, nope, that's wrong. But then, so you have to pay attention to what they're asking. They'll ask one of those two things, standard error or margin of error. If it's standard error, then you don't need the t critical value times it. Anybody have the answer here? 9.3 what? 1.6. And that's just the standard error, right?
Yeah.
So the margin of error that they want us to enter is 9.316 times 2.145. Read that number to me.
19.98.
19 I need 6 decimal places.
9, 8, 36, 35.
9, 8, 3, 6, 3, 5. Now, I was not careful. This quite likely is going to say not correct. Nope, it did. It took it. I was worried that we weren't keeping enough decimal places here. So I wasn't careful about it because I was in a hurry. But when you look ahead and it's saying keep 6 decimal places, then you need to keep at least 6 in each of these steps. Right? But apparently they've got some fuzz factor built in, so it's okay. All right? So we didn't get to do the third step, which just says now get the interval. But you would take the point estimate, add and subtract that margin of error that you just entered, and you got the interval. Right? And it should match what you get out of your calculator from that 2 samp t int. All right, we'll see you next time.